if a single displacement was a first date at Arby's gone horribly awry, a double displacement reaction is a little bit odder, right? Or a little bit more unexpected. Maybe you go on a double date. Maybe it's a double date gone strange. You know, maybe we've got Jim, and Jim's on a date with, who's Jim on a date with? Janet? Okay. And there we have Janet. And Jim and Janet are good friends with, who's another couple? Who? Pamela. Okay, we've got Pamela. And who is Pamela on a date with? And Jack. Okay, sure. I need a different color. You know what? That's a nice color. Okay, Jack, we said. You know, my usual rule is to avoid the names of students currently in this class, and I think that's a good policy. So somebody give me a different name. Was it? Roy. Okay. I don't like that one because I have a speech impediment and the letter R is hard for me, but you know what? For you guys, all right, we'll do it. I tend to avoid words that start or end with the letter R as much as humanly possible because it comes out as like Roy. But that's okay. For you, I'm on it. What do we got? What's going to happen if this is a double displacement reaction, right? So right now, what we have here is a couple, right, of Jim and Janet. And here we have a couple of Pamela and Roy. And they go on a double date. And, you know, as they're sitting, as one does at Arby's, enjoying, you know, a delicious roundup meal of beef and cheddar and those curly fries, the curly fries. And, you know, Pepsi products, a lesser thing, right? Like, so they're a Pepsi product place. And as a rule, that's not good. I don't approve. Except the thing is, if it's Pepsi product place and they have the Dr. Pepper, now you're winning. Dr. Pepper, delicious, an underdrank soda pop. This is my opinion. So they're sitting having that. And Jim is ranting and raving and waxing rhapsodic as one does about curly fries and Dr. Pepper. And Janet is thinking, oh my God, I can't believe we're talking about curly fries and Dr. Pepper again. And Roy is like, I thought I was the only one. I didn't realize Jim loved Dr. Pepper and curly fries. And they kind of start looking into each other's eyes a little bit longingly. And by the end of the evening, what has happened? What have we discovered on this illustrious double date? Sorry? They're in love with each other. Turns out Jim and Roy, God, where have you been all my life, Roy? I don't know, Jim. Where have you been all my life? They're a couple now. And isn't that romantic? Indeed it is. Because now, all it takes, one little date, Jim and Janet, no more. There's no more Jim and Janet. We got ourselves a Jim and Roy. And that could be really sad, except the whole time this is going on, Janet is thinking, oh my God, I can't believe I'm sitting here talking about Arby's when I could be watching rugby. And at one point lets this slip, which is rude, and we can all agree that was rude. And what do we discover about Pamela? Also loves rugby. In fact, plays rugby. Janet doesn't. Janet's just a fan. But Pam plays rugby, and they get talking about this, and they discover a mutual love for the sport of rugby, which is the correct decision, because rugby is a superior sport to most others, except baseball, which is the perfect sport. But, you know, there we are. And as they've discovered this, what has happened also by the end of the night? We got ourselves another new couple, team. And this new couple is Pamela and Janet. Or if you prefer, Pam and Jan. Pam and Jan, right? Pam and Jan. And what I like about this one, as opposed, because to me a single displacement reaction feels so upsetting, right? Like a single displacement reaction, you're like, geez, that poor guy just got dumped in an Arby's for somebody working at an Arby's. That's sad. You know what I'm saying? I'm not saying it dredges up memories necessarily, but feelings, right? One can empathize, one can sympathize, but this is just kind of life working out as life works out. As they say, all is fair in love and war. And I don't know about war, but in love, sure. And here we go. So what has happened, notably, is that everyone had a partner at the beginning of the date. Everyone has a partner at the end of the date. That's good, right? The difference is that they have swapped partners, right? So there we are. And not in some lurid way either. This is chaste. We're just talking a mutual love of rugby and or curly fries and Dr. Pepper. A superior sport and a superior soda. This is my hot take. More generally speaking, the general form of a double displacement reaction is this. We have some compound A and B, and it doesn't matter how many of each, right? And it reacts with some compound, and we'll say C and D, and again, it doesn't matter how many of each. And once they have reacted, what are together on the other side? That's right, A and D. And again, it doesn't matter how many of each. And yeah, and I'm going to put it in the order CB because that's going to be consistent with what we've been considering, so the metal involved and the non-metal involved. Does that make sense? We have a convention. Because what won't happen is you're not going to have a double displacement reaction where at the end you have two negative ions together and two positive ions together. It's important to remember opposites still attract, right? So you're not ever going to do this and end up with nitrogen oxide and sodium berylliide, right? You're not going to get two positive things stuck together and two negative things stuck together. They will swap partners, but they will swap partners in such a way that you still have a positive and a negative couple and a positive and a negative couple. Okay, so let's look at an example. Exempla gratia uno. And let's say, what do I want to say? Let's say sodium carbonate reacts with, and let's say calcium chloride. Now, if you recall, I said during Unit 1 that all those Unit 1 skills were never going to go away, right? That we're just going to be using them every day. Well, here we are. Because the first thing we need to figure out is, what are these things, right? So, what is sodium carbonate? Sodium is what? Na. How many electrons does sodium want to give away? 1. Which means that one of them would give away 1 electron, 2 of them would give away 2 electrons, 3 of them would give away 3 electrons, etc., etc., etc. What is carbonate? CO3. Does anyone remember what charge it takes? We can look it up. It is -2. Very good. Which means in forming, one of them would accept 2 electrons, 2 of them would accept 4, 3 of them would accept 6. Where's the matchup happen? What's the formula? Okay, very good. So sodium carbonate is Na2CO3. Okay. What's it going to react with? Calcium chloride. What's calcium? Ca plus 2, good. Which means that 1 calcium will give away 2 electrons, 2 of them would give away 4, 3 of them would give away 6, etc., etc. What is chloride? Yeah, just Cl. It's not chlorate, it's not chlorite, it's not any of those. It's just chloride, so it's just from the periodic table. And if we look up at the periodic table, chloride takes a charge of -1, so one of them would take 1 electron, 2 would take 2, 3 would take 3, etc., etc. What's the formula of calcium chloride? Where does it balance? CaCl2. Very good. So you can see why these are a little time consuming, right? You got to figure the formula out for everything. You can't just take it on the name. You got to figure out the formula for everything. Now, if this is our date, who is sodium on a date with right now? Who's sodium on a date with right now? Carbonate. And they're talking, God, Carbonate just will not shut up about this history class he's been taking at school and all about like Byzantine history. And Sodium is thinking like, oh my God, I can't believe this. I could be washing my hair right now, right? And who is calcium on a date with? Yeah, very good. Calcium's on a date with chlorine, right? And they are also having some conversation they are not interested in. At the other end of the date, who's going to be with who? On the other side of the date, who's sodium going to be with? Chlorine, chloride, good. And who's calcium going to be with? Carbonate, good. Now, we can figure that out then. Sodium, on the other side of this, we have to figure the formula out. Can I just say that it will be Na2Cl2? Can I just take the numbers with them? You got to work it out. So sodium wants to give away how many electrons when it forms? And chlorine wants to take how many? 1. And do I even need to make a chart for that? No, that works nicely, right? So what is the formula for sodium chloride? Yeah, but you'll see in my mind, coming up with the name first is actually really helpful, right? If you know the name, then you can go figure it out. So yeah, the name is sodium chloride, the formula NaCl. What will the other product be? Just its name. Calcium carbonate. Calcium carbonate is chalk and various other things. It's a very common, stone that we see. I believe it's limestone is mostly calcium carbonate. What charge does calcium take? +2, which means that one of them will give away 2 electrons, 2 of them will give away 4, 3 of them will give away 6, etc., etc. And carbonate, we said, was what? CO3. And what charge does it take? -2, and so I didn't need to bother with any of that. What's the formula of this? CaCO3. Very good. And we're done and we can move on? Question mark? No. Balance. This is not balanced. How do we balance it? Okay, so we need a 2 here to balance the sodiums out. And that also balances out chlorine. Is calcium balanced? Yep. Is carbonate balanced? Yep. So we're happy campers, right? So there's our reaction. Pretty good, right? Okay. How's that feel? Not too bad? We could do 10 more examples like that. But here's my question. Example 2. NaCl reacts with CaCO3. Wait a minute. What's going on? NaCl reacts with CaCO3. You will recognize these as what we ended up with last time. Will they react? Will they go back? Will they swap partners again? Or is this a permanent swap? The next date they go on, will Jim and Ray end up breaking up and Jim and Janet end up back together? Or is this for good? I mean, who knows, right? Winds of change, all these things, lots can happen. But I'll tell you this, Jim and Janet aren't getting back together. Oh, they're done. They're done. Will sodium go back to carbonate? And will calcium go back to chloride? Or did that last reaction actually happen? Do you know what I'm saying? Like, will this reaction undo itself? With single displacement, how did we check? With single displacement, how do we check if the reaction will happen or not? We check the activity series. Can we do that here? Okay. Can sodium kick out calcium? Sodium's right near the top of the activity series. I think it's like the third thing down, second thing down. It's right up there. Calcium's above it? Okay, so sodium can't kick out calcium, right? So calcium can kick out sodium. So this will happen? Do you see what I'm saying here? Like, how would you know which one's kicking which one out? You wouldn't, right? Does that make sense? So we can't use the activity series. As it happens, this doesn't happen. We get no reaction. So the question is, why? Why does Na2CO3 plus CaCl happen, but NaCl plus CaCO3 does not? Why? And the answer is it can't be because of the activity series. Because the activity series is the idea of one thing kicking another thing out. But that's not what's happening here. Here we're talking about two things that are already ions swapping partners, right? So what does happen is it's not related to the activity series. Instead, it's related to solubility. Now, we did a lab on this. What does it mean for something to be soluble?
It dissolves in water.
Yeah. Does it dissolve in water? And by the way, it doesn't actually just mean water. Solubility means does it dissolve in something? In this class, we're going to work with solubility in water. If you do advanced chemistry, you'll work sometimes with alcohols as solvents and terpenes as all kinds of things as solvents. But we're going to use water as our solvent. It's safe, it's plentiful, it's available. It's the thing we normally work with in most basic chemistry. Though certainly it's not the only solvent we work with. So here's the idea. A double displacement reaction will occur if at least one of the products of the reaction is insoluble. When we do our solution chemistry unit a couple of units from now, we will really break into why this is true. For now, you're just going to have to trust me that it's true. Is that fair? So if we go back to our previous example, sodium carbonate dissolves in water, which means it can be aqueous. And calcium chloride dissolves in water, which means that it can be defined as aqueous. And we said we needed two sodium chlorides on the other side. Sodium chloride dissolves in water. That means that right now, you take something that is a solution, you mix it with something else that is a solution, and on the other end you get a solution. But now, what was the next product? Calcium chloride. And the thing about calcium chloride is it is limestone. It's chalk. Yep. Or calcium carbonate, rather. Thank you. Sorry. Calcium carbonate. Calcium carbonate is chalk. It's a rock. It's a mineral. And you get chalk wet. Does it dissolve? It gets mushy sometimes, but it's not going to dissolve. It's a rock that if you dissolve in water, it barely dissolves at all. It mostly stays solid. Now, if you think about it, look at that. You can tell why that makes this a reaction, right? If this also stayed dissolved, then what your reaction would look like is you take something that's dissolved, mix it with something that's dissolved, and everything stays dissolved. That's not a reaction. Does that make sense? But here, you mix two things that are dissolved, and one of your products is solid. That is a change. That's a reaction. Does that make sense? So the appearance of a solid makes this a reaction. By the way, we call that, and I hate this term because we're used to this meaning a liquid falling out of the sky, so this term is so stupid. But they call this a precipitate. Again, that's a really bad choice of words because we think of precipitation being liquids falling, right? I don't know what to tell you. But when a solid forms out of liquids, we call that a precipitate. The solid is called the precipitate. So for a double displacement reaction to happen, one of its products has to be insoluble. So how do you know? You can look up the solubility of any compound. There's a million sources. A great one is Wikipedia. Wikipedia's solubility table is really big. It's got just about everything in it, and it's free, and you already know how to get there. There are other sources, but if I'm doing this, and there's stuff that's going to be tricky to work with, I just open up Wikipedia. And so to show you here, if I went to Wikipedia solubility table, here's the solubility table. And do you see how this is just, it tells us how many grams of something per milliliter, per 100 mils, will dissolve at various temperatures. And we usually say that if it's below a gram, we would define that as just not soluble. Does that make sense? So we could look, and this lab involved our products. You only have to worry about your products. We don't care about our reactants, right? Our first product here is sodium chloride. And if we look up sodium chloride, you'll see that its solubility is really big, right? Salt dissolves pretty well. In fact, in 100 mils of water at room temperature, you should be able to dissolve how many grams of salt? Like 36 grams, right? That's a lot. Does that make sense? So sodium chloride, like we said, it's aqueous. It dissolves. The other one was calcium carbonate, right? So we can search for that. Calcium carbonate. And if you look here, it's giving us a little bit of scientific notation, but 7.7 times 10 to the negative 4. We haven't reviewed scientific notation yet, but is that a big number? Times 10 to a negative exponent? No, that's a really small number, which means calcium carbonate is basically insoluble. Does that make sense? So we have to say here, it's not going to be dissolved. It's going to be a solid. So you can just look any of these up if you want. Does that make sense? Now, that is not always going to be the quickest, easiest thing, but that will work. You can do that. Right? So we could look that up. You don't obviously have to draw this, but when you go look back at this note, we can say that's a small number. So CaCO3, solid, not aqueous, right? Is that comfortable? Does that make sense? Now, if you ever can't figure out the solubility of something, just find it, right? If it's not on the Wikipedia table, then you can look the thing up on PubChem, which is a public chemistry database, and it will for sure have its solubility in water. That's just a harder website to navigate, so it's not the first place I go, but it's an even better list than that Wikipedia one. But for most things, we don't have to look it up like that. For most things, and I will print one of these for you tomorrow. Sorry, I meant to have them printed today, and I forgot. Oh, where is it? I will find it for you after. Now I'm lost. We have a quick guideline of solubility rules, which I will show you. Boy, I am offline. Everything is annoying today. Do you ever have a day where just everything is annoying? Today is a day where everything I go to do is a little bit annoying, but that's okay. So if I looked at last year's unit test for this unit, oh, look at that. Ripped straight from the notes. Did I seriously not give you a solubility table last year? What am I doing? Hold on. Solubility table. Yeah. So you listen, do not write this. I'll give you a copy of this. Okay. Don't try to copy this right now. But we have a little table here that gives you the most common things. This is common trends in solubility. It won't tell you exactly for everything, but can we read this together? This says that if something is a nitrate, no matter what the other thing is, sodium nitrate, calcium nitrate, lithium nitrate, mercury nitrate, copper nitrate, doesn't matter. They are always, are there any exceptions to that? None whatsoever. So every nitrate will dissolve in water. This is a perchlorate, and perchlorates are always soluble. Are there any exceptions? No. On the other hand, chlorides are mostly soluble. So that's why our calcium chloride dissolved, because chlorides are mostly soluble. The only exceptions to that are, not quite, silver, yeah, Hg, mercury, Pb, lead. Does that make sense? So lead chloride doesn't dissolve, but every other chloride other than mercury, silver, or lead mostly does. Again, this doesn't cover everything, but it covers all the most common things. This is just a set of trends. It's not a specific rule. By the way, if you look at our calcium carbonate, calcium is, or carbonates rather, are insoluble. They don't dissolve. They will stay solid. The only exceptions are group 1A, which if you look here is, so hydrogen carbonate will dissolve, lithium carbonate, sodium carbonate, potassium carbonate, rubidium carbonate, cesium carbonate, francium carbonate, and NH4, which if you remember from your table is ammonium. Ammonium carbonate will dissolve, but all the other ones are insoluble. They will stay solid. Does that make sense? And that means that calcium carbonate is insoluble, which is why that reaction happened, because it gave us an insoluble product. Does that make sense? I'm going to name a compound right now, and I want you to tell me whether it's soluble or not. Are they soluble? Let's say, I don't know. A, lead iodide. B, let's say potassium phosphate. C, copper 2 hydroxide. So just take a minute, look at my chart here. Again, I'll give you a copy of this and see if you can find those. See if you can read that chart. Yeah. It actually doesn't matter. And by the way, when this says lead, it means lead in general, so that would be true for the 4 plus as well. But in this case, we'll call it lead 2 iodide. Sorry about that. So take a minute, see if you can spot them. What do we think? This first one, lead iodide. Where should I be looking in here to see if that is soluble or not? Don't give me the answer. Tell me where I should look. Krish? Yeah, we'd look at the iodides, which is this row here, and it tells us that iodides are typically soluble. So this would typically be aqueous. But what are the exceptions? Silver, mercury, or lead. So not aqueous then. And if it's not aqueous, what will it be? Either a solid, liquid, or a gas. And here we're talking about an ionic compound, so it's going to be a solid, right? Good. Where should I be looking for this one, potassium phosphate? Yeah, we can actually look at 2 rules. The first rule is we can look at potassium, and it tells us that potassium is soluble, and exceptions? None. So right there, that will tell us this has to be aqueous. It has to be soluble. On the other hand, we also could have looked in the phosphate row, and phosphates are actually typically not soluble. Is that a contradiction? Well, it's not, because it says the exception is everything in Group 1. And where's potassium? In group 1. So those two rules agree. So that will dissolve. So how would we show that? AQ for aqueous, right? What about copper 2 hydroxide? Where am I looking for that rule? We're going to look in hydroxides, which is here. And they, as a rule, are not soluble. So as a rule, this would be a solid, though there are exceptions. So we should check the exceptions. And the exceptions are group 1A. Is copper in group 1A? No. Calcium. Is copper calcium?
No.
It is not. Barium. Is copper barium?
No.
It is not. Strontium. Is copper strontium? No. So copper 2 hydroxide will be a solid. Does that make sense? Now again, if you can't figure out, looking at this, what something's solubility is, then where do we go? Just go to Wikipedia and look it up. Does that make sense? If there's something you can't figure out with this, it doesn't mean you're off the hook. It just means just go use a bigger... do I have NIST out here? When I was your age, we didn't have Wikipedia. We had the CRC Handbook of Physics and Chemistry. And if we wanted to know if something was soluble or not, we'd look it up in a book. Right? This is all the physical properties of all the chemicals you could want in tables, ready and waiting for you. And the truth is, you might think that sounds miserable, but it actually was much easier because it was reliable and you knew where it was. And you got pretty quick with looking through here and you could get there really in a hurry. So if I wanted to know the thermodynamic properties of oxides, boy, sign me up. Here's the thermodynamic. If I want to know the values of chemical thermodynamic properties of hydrocarbons, oh, have I got your back? What if you want to know the vapor pressures, critical temperatures, and critical pressures of organic compounds? Oh, I've got you. So anyway, now you just go to Wikipedia. We'll be there. But for God's sakes, if you get it wrong and you tell me, well, I asked ChatGPT, I will throw my coffee at you. And it might be hot. You don't know. It could be early in the day. Also, ChatGPT just, signed a deal with the U.S. government to provide AI services for military operations. I don't know what your feelings are on that, but my feelings are I already didn't like AI, and now I'm very much on board. If you're going to use AI, at least use like Anthropic. What's theirs? Claude. At least they refused to be a part of, using AI to kill people remotely. Anyway, do with that what you will. But that's my standing on my soapbox for 5 minutes. I don't know how you feel about having computers with autonomous brains controlling military-grade weapons. My instinct is that seems like a science fiction movie that I've seen a few too many times, and you'd think we'd be a little smarter than that. But fun fact about people, anytime you find yourself saying, you'd think we'd be a little bit smarter than that, you know what you discover? Boy, we're just not. We're just not smarter than that, team, and I don't know why. So listen, here's the basic idea. If you mix, and you don't have to draw this if the visual isn't, especially drawn by me, if the visual isn't helpful to you, but say you have a compound here, all right, so we have a compound, and it is an aqueous solution. So here is compound A, all right? We'll call that AB. And then let's say we have a second compound, and we mix it together, right? And let's say that this one is CD, right? If we mix them together, all right, into a bigger flask, all right, if we just mix these two together and put them into a bigger flask, and they just stay a liquid, kind of like that. I didn't pick my colors well, where if I made that pink and then mix them together and it's kind of purpley, that would actually make some kind of sense. And never let it be said I went out of my way to make sense, but I'm not opposed in the interregnum. If this is just A, D, and CB, but they're still aqueous, we say that isn't a reaction. Does that make sense? That's no reaction. Nothing happened. We just mixed them. Which, when you think about it, actually makes sense. If you mix two things together and they just sit there, we would all agree that's nothing happening, right? Is everyone comfortable with that? On the other, so if both the products are aqueous, no reaction, nothing happened. But on the other hand, versus we take these two beakers, so we've got our beaker with AB in it, and we've got our beaker with CD in it. We put those together, and we get our bigger, these aren't beakers, they're flasks, and I don't know why nobody's correcting me on that, but that's okay. So if we take AB and we react it with CD, and all of a sudden over here, we get a new we get a solution, but more importantly, we get a big solid lump forming, right? So if we have aqueous AB reacting with aqueous CD, and what we end up with is aqueous AD, but a solid lump of CD, of CB, right? That's a reaction. Because a precipitate is formed. Now, it could also be not just, something could not dissolve and instead of forming solid, it could form a gas. What would we see then? You'd mix two things together and you would start to see if it's forming a gas. Maybe the vapor, and certainly we'd see some bubbles, right? Does that make sense? What if the thing that wasn't soluble was a liquid? Can that happen? Can it form a liquid that doesn't dissolve in the other liquid? What would that look like? You've all seen that. Like oil and water. You can sometimes actually get a reaction where you get two layers. You mix two things together and all of a sudden, whoop, a layer of liquid appears that won't mix with the other. You get two separate layers. That would also be a reaction. Does that make sense? So, this is our reaction when we get something insoluble forming. I'm going to put some homework up that just asks you to practice these, all right? And just like with the other one, there's going to be two distinct types. There's going to be some questions that ask you, will these react? And then there's going to be some questions that ask you to actually balance out the reactions. Does that make sense? So I'm going to commend that practice to you and make sure you get it done. I'm here to help you if you're struggling with it, but make sure you give it a try, all right? That's all for me.